Okay, so today's class, we are going to spend most of today's class talking about second order effects in MOSFETs, specifically short channel effects that have to do with scaling the MOSFETs. We're trying to always make the MOSFETs smaller, right? That's a key part of Moore's law. So we're going to talk a little bit about some of these short channel effects that occur in MOSFETs. We'll also talk about the body effect, which doesn't necessarily have to occur in a short channel device. But before we do that, we are going to talk about, just touch again on threshold voltages, because that's where we ended up last time. So I want to briefly remind you of the different factors that are involved in threshold voltages, and then we'll go on to short channel effects, and then I'm going to talk to you today about how a transistor is fabricated. Very basic overview of the different steps that goes into fabricating a MOSFET. That's important because, in my opinion, the technologies that are used to fabricate a MOSFET are just important as the physics of the device itself. One of the reasons why the MOSFET has gained so much popularity and is used ubiquitously in all the electronics is basically because we've perfected ways to make them. We've perfected ways to make them very, very small. And that's what allows us to have so much computational complexity in our devices. So the threshold voltage, we touched on that last time. I want to finish that up before we get into the second order effects, and that's going to be most of today. So threshold voltage is a very important parameter in a MOSFET. Okay, the threshold voltage has to be, if we think about a couple, practical things. If you're running your MOSFET off a 3.6 volt lithium ion rechargeable battery, the threshold voltages can't be more than 3.6 volts, right? That's one issue. Your threshold voltages can't be greater than the supply voltages in the system. Second thing is, it turns out that when you're dealing with large threshold voltages, your MOSFETs require more power. Right. So there's an incentive to actually use lower threshold voltages. Okay, that's a second practical issue. Some of you may have seen like some of these, the MOSFET devices that are used in the Intel Atom processors, the mobile processors. Those are low voltage transistors. Sometimes they work at like around 1 volt, a little bit above. Some of them work below 1 volt. So low voltages can save power. A third practical issue is that the threshold voltages have to be uniform for all the MOSFETs in your system. You figure one chip, okay, we went over this at the beginning of the module. A typical chip has something like a few billion transistors. An Intel multi-core processor has a few billion transistors. An NVIDIA GPU has something like 22 billion transistors. It's insane. Now, if you're making that many, if the number of transistors on your device is greater than the world population, it's one of the challenges is making sure all those devices work, right? So this threshold voltage is very important in all those devices. If you're going to make digital logic gates or you're going to make analog circuits, you want to make sure that the threshold voltages across all the transistors on your wafer are relatively uniform. Okay, so we're going to touch on ways of controlling threshold voltages, but let's remind ourselves what the equations are. A threshold voltage for a standard MOSFET device that we've talked about in this class, it has three components to it. The flatband voltage, then this depletion charge, or this is often called the voltage drop due to the depletion region. And then the third component is the requirement of strong inversion. So we're going to just run through these real quick from the right to the left. So the first requirement is strong inversion. We said that in order for a MOSFET to be on, you have to create an inversion channel. All right, that was this guy here. All right, you apply a positive gate voltage that has the electric field. You push away the holes in the substrate, in a p-type substrate. You pull in the electrons, and that creates this inversion channel. All right, well, we talked about this in terms of the energy band diagram. I'm going to jump back down to where I was earlier. In order for you to have strong inversion, this is the energy band diagram. This left side is showing the oxide region, and then this is the semiconductor, and then metal is over here on the left. So this is the semiconductor. You can see that it's a p-type semiconductor out here where the mouse is, right? And we know it's a p-type semiconductor because EF is lower than EI. So it's a p-type semiconductor. We have holes. In order to get strong inversion, what you want to do is you want this band to bend by an amount equal to 2 times this. Okay, so the rationale behind that is that we have a p-type material out in the substrate, and what defines how p-type the material is this distance here, right? If this distance is large, if EI minus EF is large, is it more p-type or less p-type?
If it's large?
Yeah, let's say that Q phi F gets large.
It's more p-type.
It's more p-type. We have more hole concentration, right? Okay, so what we want to do is we want to make the material n-type at the interface. Okay, and how do we know it's n-type? Because EI is less than EF now. All right, this is the key part. This blue dotted line here is the Fermi level. And EI is now below EF, okay? That's how we know that the material has been inverted. Yeah, I just showed you the physical model. I said the electrons get pulled in, right? So you have an n-type material. The energy band model is saying the same thing, except in a different language. EI is below EF. That means we have a low hole concentration, a large electron concentration. Okay? So what we want to do is we want to make the material n-type at the interface. And how n-type do we want it to be? We want it to be as n-type as the rest of the substrate is p-type, if that makes sense. And nodding. So the way it looks in the diagram is that this distance here, EI minus EF in the substrate, has to equal this distance here. So the distance from the blue line to the black line here is the same as the distance from the blue line to the black line here. Okay. So the amount of bending has to equal 2 times Q phi F, twice this. So the amount of bending is denoted as Q phi S, and that has to equal twice this amount here. All right. So that is saying that is indicating that we have strong inversion. We have a strong n-type channel near the interface. The second part, I'm probably going into maybe it's fine to review. We've had like a week since the last class. The second factor was a voltage drop due to the depletion charge, and the simple way to explain this was that you have a capacitor here. What we're interested in is how much VGS is required to create strong inversion. So this VGS has to be greater than VT. So there's a voltage drop going from the metal to the body here. Okay, this forms a capacitor. So there's some voltage drop across this oxide here. Okay, and there's some voltage drop across this depletion region here. All right, so in the previous slide, we talked about how much voltage drop is necessary just across this region in order to form an inversion channel. That bending of the diagram that I showed you earlier, that's a voltage drop, right? Bending of the diagrams corresponds to electric field, and that corresponds to a voltage drop. So there's some voltage drop that's occurring right there near the interface. There's another voltage drop that's occurring across the capacitor. And if you look at the relationship for a capacitor, the voltage drop across a capacitor is given by the equation Q equals CV. It's one of the first equations that you learn about in a capacitor. So this is just a rearranged form of Q equals CV. All right, this V is equal to Q over C. And specifically what that means is that the voltage drop due to due to this depletion charge here that you can see, there's a set of depletion charge in the semiconductor substrate. So that is negative. And then there's an equal amount of positive charge built up on the other side of the capacitor. So these are the positive charges and these are the negative charges on the two sides of the insulating material, which is the oxide. All right, so that oxide has a certain capacitance associated with it. The unit capacitance is given by epsilon over D. All right, so what does that tell you about the capacitance? Well, the thinner you make your gate oxide, the larger your capacitance is going to be. All right, that's an important point that we'll come back to in a little bit. All right, but the voltage drop across the capacitor is equal to QD divided by CI. Okay, and that's the second term in this in the threshold voltage equation. So QD over CI, and this term is positive for an NMOS device, negative for a PMOS device. So for an NMOS device, it actually reduces the threshold voltage for an NMOS device. Okay, because you have a negative sign, and then this term here, QD over CI, is positive for an NMOS device. All right, so okay, so the third thing is the voltage drop due to the flatband voltage. All right, so you have your energy band diagrams here, some of the stuff that you've seen earlier, and one of the things that we talked about in class last time is that phi m is not necessarily equal to phi s, as was shown in the first diagram, the first energy band diagram that we showed. Now, a phi m is typically quite different than ms, the phi s. So phi m is a metal work function, phi s is a semiconductor work function. This energy band diagram shows the metal, the oxide, and the semiconductor at equilibrium. So how do I know it's at equilibrium? This Fermi level is a straight line across like this. All right. So in this case, the phi m is less than phi s, and because of that, because there's a difference in phi m and phi s, there's a bending of the band diagram here, and then this results in an electron buildup even at equilibrium. So what does that mean? Does that mean your device is on or off at equilibrium? If you have a bunch of electrons here, and notice that EI is less than EF here. Do we have inversion here?
No.
Okay, yes and no, I heard both. Why or why not? Let's talk about that.
Since there is a bending greater than EF, there is an inversion.
Yes. Exactly. Because this band has bent enough where now you have inverted the material, meaning it's below EF. So that means, yes, you have an inversion channel there. And it's also, this diagram also shows that you have a buildup of electrons there. All right. So this diagram is showing you that if the semiconductor work function is significantly larger than the metal work function, you could get an inversion channel without applying a gate voltage to the material. That means the device is on all the time. Does anyone know what kind of device that is?
It's almost to the enhanced.
Yes, it's the depletion mode device. Depletion mode device is the device that's on even when there's no voltage, when no gate voltage applied. Right, so this is why you have to choose your metal and semiconductor work functions pretty carefully. The second part of the flatband voltage that comes into account has to do with the cleanliness of the manufacturing process. If you have typically, if you have a very clean manufacturing process, there will not be any ions trapped in the silicon oxide in the gate material. Okay, but if you're using processes that have, for example, if you're rinsing the wafer in water that is not completely deionized, there's a chance that some of those ions can embed themselves into the gate material, and those will totally change your threshold voltages. And I think I mentioned this in class last time, but these charges actually made things very difficult when they were trying to make MOSFETs initially. This is one of the big challenges, and that's one of the reasons why dry etching processes are used more often than wet etching processes nowadays, because with the dry etching processes, you don't have, you're not putting it in liquids that have ions, ions in them. So these charges, anytime you have charges, that impacts electric field, and that electric field ultimately changes the threshold voltages. How much does it affect the threshold voltage? This is the same formula as what you saw earlier. Whenever you have charge, the voltage associated with that charge is Q over C. All right, notice that this is, instead of QD, this is just QI over CI. So you're creating additional charge in the dielectric, and that's creating an additional voltage drop. Actually, notice that this is if you have the charge is positive. If the charge is positive, then you're actually going to end up reducing your flatband voltage. You'll end up reducing your threshold voltages. Okay. So you'll become familiar with these equations if you use them in a problem. The problems are posted today. I suggest you go over them. These are typical values of phi ms when we use a polysilicon doped gate. So I didn't talk about this too much last time, so I just want to mention it again. Why is a polysilicon gate, why were polysilicon gates used pretty frequently? Well, the standard model of the MOSFET, we have this metal, and then we have the gate material, and then the semiconductor, right? Well, when you're actually manufacturing the device, I'll go over the manufacturing process in a little bit. The issue with the metal is that it has to be able to withstand high temperature processes. Some of the earlier processes that were used to make the source and the drain regions, and ultimately the oxide regions, and then the gate, and then the additional metallization layers, some of them required high temperature processes, and a lot of metals can't withstand high temperatures. For example, aluminum melts at high temperatures. So instead what they did is they used a silicon material which silicon has a very high melting temperature, and they just used a heavily doped silicon material. They call it polysilicon. Polysilicon means it's not single crystal silicon. It's partly amorphous. It's partly single crystal. Okay, and the fact that it's amorphous, it doesn't matter. It's just behaving as a metal. It just has to be very conductive. So as long as it's highly doped, is good enough. Okay, we don't need to rely on the single crystal properties of that. So when they're using polysilicon gates, they've done a lot of empirical studies to find out, that as you change the doping levels, because as you change the doping levels, the phi ms changes. So it changes the work function of the polysilicon, and then also changes the work function of the substrate. I'll get into that in a second. And this is a graph of the typical threshold voltages, and this is showing an important control method, which is showing essentially that as you increase the substrate doping, the threshold voltages increase for an N-channel device, and then they decrease for a P-channel device. So the question is why? If you want to make sure that you understand why, part of it is due to the metal semiconductor work function. So let's look at a typical N-channel device. Okay, and a typical N-channel device will have a P-type substrate and an N-plus polysilicon gate. What's happening here is that the phi ms is actually going down with increased doping, but the actual threshold voltage is increasing here. So you might wonder why these are going in opposite directions. This is because as you increase the threshold voltage, as you increase the substrate doping, what's happening is, let me back up here. As you're increasing the substrate doping, this term is increasing, this 2 phi f term is increasing, because remember the 2 phi f term is this distance right here. So if you increase the doping of the p-type substrate, this distance is going to increase. The Fermi level is going to go down, right? So the higher you dope the p-type substrate, this q phi f term is going to become larger. So as you increase the doping, this term increases. And as you increase the doping, the depletion charge also increases. Okay, and the depletion charge, this term is positive for an NMOS device, so that will end up increasing your threshold voltages. So even though your flatband voltage is going down, ultimately the threshold voltage increases. All right, so I'm going to talk a little bit about the methods of controlling VT. This slide, as you saw earlier, this is just an example of calculating the threshold voltages. If we have time at the end of class, we can do it today or Wednesday, but this is just one of the problems that I would like for you all to do as in your homework, so that you can get used to doing those types of calculations. I added this slide just to talk to you a little bit about the practical issues of controlling threshold voltages. And this gets back to what I was talking about just a little earlier about how do we ensure that of all the billion of transistors that we have on the chip, how do we ensure that they have similar threshold voltages, and how can we control the threshold voltages very, very precisely? Because all the circuit designers in a chip team, they're relying on the process engineers to be able to create reliable threshold voltages. Some of you have used SPICE, SPICE simulations and things like that. Circuit designers need to know what that threshold voltage is going to be, whether you're doing digital or analog design. So these are some methods of controlling the threshold voltages which are used in practice. The phi ms is starting with that. This can be adjusted by choosing the gate material. I mentioned before that polysilicon has been traditionally used for many years because it has a high melting point. And so instead of using a low melting point metal, you use polysilicon, which is compatible with these high temperature processes. And because the polysilicon is doped to a very high degree, it behaves like a metal. All right? And when you're using polysilicon, this is the type of chart that you would use to basically figure out what the metal semiconductor work function is. It's a function of the doping process. The same process that you're using to dope the polysilicon, is also going to end up doping the substrate as well. So the doping step controls both phi m and phi s in a polysilicon type process. More recently meaning like 2007, so it's not that recent, they started using metals again, and this is because there were some innovations in the type of metal. The metals have higher melting points, and they also use lower temperature processes after the metal deposition. So that allowed them to use metal gates instead of polysilicon. And then in conjunction with that, they used high K dielectrics. So I'll talk about that in a second. But the first and foremost way of controlling VT is by controlling the metal semiconductor work function. So the metal work function depends on the choice of metal. The semiconductor work function depends on the doping of the semiconductor, right? So both of these can be controlled. Phi F, that's strictly a function of the substrate doping, the semiconductor doping. You dope it high, phi F gets larger. You dope it lower, phi F goes lower. Qi depends on the oxidation conditions. I mentioned to you the Qi are those trapped charges, the charges trapped in the oxide. So if you had unclean processes, that could inadvertently put Qi into the oxide, and that would change your threshold voltages. On the other hand, sometimes if you intentionally would like to introduce charges into there, that can also be done in a way that the Qi is controlled to some extent, and that can change your threshold voltages. The next one is Ci. Now, Ci is the oxide capacitance. This is an important term because this is something that is typically controlled to a great degree in semiconductor fabrication. It's a very important one. So Ci is equal to epsilon oxide divided by the thickness of the oxide. We saw that a few slides earlier. So if we think about a parallel plate capacitor, what are these terms? A typical parallel plate capacitor, you have a metal, then dielectric, then another metal, right? It's a dielectric sandwich between two metals. The thickness of the dielectric and the dielectric constant of that dielectric material determines the capacitor properties. So epsilon oxide, that's the dielectric constant of the oxide material. That's determined by what material you use. And then Tox is the thickness of that oxide material. All right, notice that the Tox is on the denominator. So what happens if you go to thinner oxides? What happens to the capacitance?
Increase.
It increases. It can increase quite substantially.
How did they eliminate the overlapping area between the two electrons? Like this is epsilon A over T. This is how
Epsilon A over T. That's right.
So here they consider that A is 1.
Oh, the area of the capacitance. Yeah, that's a good question. So we are saying that this is unit capacitance. So CI stands for capacitance per unit area.
Okay.
Yeah, to actually calculate the capacitance in farads, they use picofarads or femtofarads. You would actually have to multiply by the area of the device. But this is a unit capacitance. Good question. So the CI is a good way to control the threshold voltages. If you have a small oxide thickness, that makes your capacitance very large. And that allows you to better control the gate, the material right underneath the gate. All right, and I want you to think about this intuitively. Okay, if you just imagine, let's just zoom in on this image of a semiconductor here. Right, imagine that there are positive charges deposited on the gate, and then you have the negative charges on the other side of the gate. Right. If the gate's super thin, then the positive and negative charges are close to each other, right? So it's an easier way to communicate to the other side of the gate. On the other hand, if your gate's like 10 meters thick, if you deposit positive charge on one side, there's really no hope you're going to get any kind of negative charge on the other side. So the intuition here is that the thinner the gate, the better the gate voltage can control the channel underneath the gate. Okay? And the mathematical way of thinking about it is like this. You reduce the oxide thickness, that increases the capacitance. Right? You're reducing Tox, so that increases the capacitance CI. And then the CI, if we go back to the threshold voltage equation, if we go back to the threshold voltage equation, the increasing CI makes this term smaller, so that changes the threshold voltage, right? So that becomes a way to control the threshold voltage. I personally like to think about it more in the intuitive way, like that. Like the more, the thinner your gate is, the better you're able to control that channel underneath the gate. All right, and that in fact is why there's whenever you miniaturize, whenever you try to scale down a transistor, there's always an effort to decrease the oxide thickness. All right, but there's a downside towards reducing the oxide thickness, especially when you get to very atomically thin layers, is that you start to get gate leakage currents. If we look at this picture here, this is a picture of an actual MOSFET device that Intel showed at a conference in 2007. This had a metal, a high K dielectric here, and then this was the channel region just underneath. I mean, the point of this is to show you that you can actually have very thin gate oxides that are just a few atomic layers thick. I think nowadays they're using gate oxides that are just like, a few nanometers thick. All right. So when your gate oxides become that thin, you can actually get tunneling through the gate oxide. All right. So the gate oxide is not acting as an insulator anymore. So you can actually end up getting current going through your gate. So going through here from the gate into the source. Right. One of the fundamental properties of a MOSFET is that the gate is like there's no current that goes into the gate, right? If a current goes into the gate, then your MOSFET's not behaving as it's supposed to in an ideal device. So that gate leakage is one of those issues that can occur. I'll talk more about that in a second. I'm introducing some of these ideas right now. So the solution, how do we get a high CI while reducing the thickness? The solution is to use high K dielectrics. So high K dielectrics are like dielectric materials that have a high dielectric constant. Things like, oxynitrides have a slightly higher dielectric constant than silicon, but there are other materials that have higher dielectric constants that was used by Intel for quite some time. So this is a way to achieve a large CI, which is a capacitance. And what that means ultimately is that you have more control over the gate. And large CI means you have more control over the gate. Okay. And ion implantation. So this is a last, but certainly not least, method of controlling the threshold voltage. This is typically done in most fabrication processes for CMOS devices. Now, ion implantation is an extra step that's used in the fabrication process that's used to modulate or change the threshold voltage. And what's typically done, I'm going to show you, I'm going to just zoom in here. This is showing, just look at the center part here. And in the center part here, what you're seeing is a typical structure. You have your source, gate, drain, your channel underneath here. By the way, this is an N-type substrate, and this is a P-type source and drain. Does anyone know what type of device this is? Is NMOS or PMOS?
PMOS.
It's a PMOS device. It's a PMOS device because the source and drain are both P-type, and the channel, remember that the conductive channel that's formed between the source and drain are the same type as the source and drain. So you imagine source and drain are both P-type. When you invert the material, you get a P-type conductive channel that connects the source and drain together. So this is a P-type substrate. P-type MOSFET. The substrate you can see here is N-type. Substrate is opposite of the type of device it is. So if you have an N-type substrate, that means you have a PMOS device. A P-type substrate, you have an NMOS device. Okay, but that wasn't the reason the main thing I'm going after here is talking about ion implantation. Ion implantation is a process, if you take this type of device, for example, and just imagine that you implanted extra boron atoms in the gate. Okay, the way that's typically done is that you can put there's actually a specific instrument that does boron implantation that pushes boron atoms that are in the gas phase, and it pushes it towards, blasts it into the semiconductor material through the gate material. So these boron atoms actually go through the gate material and into the region just underneath the gate. Okay, we're not going to talk about the details of how ion implantation work, but they're quite expensive machines, but they're very commonly used in the semiconductor industry. So I want to ask you then, what will happen? What will happen if we implant boron atoms into this N-type substrate? How will it affect device operation?
You will decrease the threshold because you make this area closer to the B plus.
Yeah, you got it. That's right on. Exactly what we're looking for. You see, like in a P-channel device, what in order to turn the transistor on, we have to make this material under the gate. We have to invert it to P-type, right? So by implanting some boron atoms in there already, we're already changing it partially to P-type. Okay? So as a result, it doesn't take as much voltage on the gate to create the inversion effect. You're kind of helping it. You're helping it along. It's kind of like a handicap in a golf game. You're helping it along. You don't need to apply as much voltage to the gate in order to invert the material. If you do a long ion implantation, if you do a large dose of boron atoms just underneath the gate, eventually you'll get to the point where the device is just on even without a voltage applied to it. And that is a depletion mode device, as we talked about.
So in the
Right.
N MOSFET, so we can do implant arsenide instead of the boron, and we can
Sure.
do the
Yeah, you can implant like a column 5 type dopant. The boron implant is the most commonly used one, and it's a p-type. So what it's going to do is it's going to increase the threshold voltage for an NMOS device. It's going to make it more difficult to invert the channel for an NMOS device, and for a PMOS device, it's going to make it easier to invert the channel. So it turns out that it just increases, a boron implant increases the threshold voltage, whether it's p-type or n-type. And think about that, because in a p-type device, the threshold voltage is negative, right? If you increase the threshold voltage, now the threshold voltage is becoming less negative, right? To the point where once the threshold voltage goes above 0, the PMOS device is always on, right? Now think about an NMOS device. You have a p-type substrate, and now you're implanting even more p-type material just underneath the gate. So you're making material even more p-type under the gate. So now it's going to be more difficult to invert the channel. So it's going to increase your threshold voltage. It's going to make it higher.
So would you have to do that ion implantation across the entire wafer at once to keep the threshold voltages consistent, or can you pick and choose where you do that?
You can actually pick and choose, and a lot of circuit designers will be able to will utilize the fact that you can actually control ion implantation to have you can have different threshold voltages in different parts of the wafer if you choose. Sometimes with NMOS and PMOS devices, you have two different types of devices on a typical wafer, a typical microprocessor, right? In your CMOS microprocessors rely on the fact that you have the NMOS transistor and PMOS transistor. So those NMOS and PMOS transistors may need to be implanted in different ways to control the threshold voltages as well. So you have that level of control. You can either do a global ion implant, or you can do specific regions. And the way you do specific regions is that you actually mask off certain areas. You apply it, you basically cover up certain regions and leave certain regions open.
That was
a question? Yeah. I just had to share this because this is so cool. I added this slide today. Some of you might notice I added this slide. It's not in the uploaded ones. This is one of the well-known papers that Intel presented at a conference in 2007, and it turns out that my wife's father, so my late father-in-law's, his name was on that paper. It's pretty cool.
That's cool.
Yeah, he worked at Intel for some time.
What are those ghosted lines towards the high side of the upper side of the image?
That's a good question. I'm just guessing that these are probably different metallization layers.
So is that on a PCB or an IC, or is that already installed in something?
This is actually a cross section of the MOSFET. So what they did is they took the wafer and they just cut it like this, so that you can see the cross section, the side view of the MOSFET. This is typically wouldn't be done. This transistor obviously can't be used since it's exposed. But what they do to analyze these things is that they slice it this way, and then they use high resolution microscopes. We're talking like TEMs and SEMs, like things that can, electron microscopes we talked about in module 2. You can image at super high resolution. That's what allows them to see this. My guess is that this is the metal, and then above here are other metal layers. You have your transistors, but you also need to you need to connect your transistors to other transistors, right? So they have different metallization layers. After they make all the transistors on the substrate, the next step is to create metal layers where you draw a connection, a metal trace between the source of this transistor with the drain of this transistor with the gate of another transistor. You know what I mean?
And that's all encapsulated in that little black, what we see as the processor.
Oh yeah.
And then, so that might be those ghosted lines up there?
Yeah, that's what I'm guessing.
Okay.
The way they do metallization is they alternate depositing like insulating layers and then metal layers, insulating layers and metal layers. Each metal layer is patterned. So a typical circuit designer would have up to seven layers of different metal layers where they can use to route connections between transistors. And the reason they need 7 layers, think about it, if you just had one layer, you could never have metal lines crossing over each other, right? Now, take that problem and multiply it by 1 billion. If you have 1 billion transistors and you're trying to make the right connections and you want to make sure that your metal lines never cross over each other, you don't just need 2 metal layers. It turns out you need like 4, 5, 6, 7, even more. I don't know exactly how many metal layers they use in the high-end microprocessors today. Typically, a lot of that metal routing is done through computer algorithms.
So those are like wires then?
They're wires. They're essentially wires, yeah. And so you deposit a metal layer, you pattern it, you deposit an insulating layer on top of it, because you can't have 2 metal layers touching each other, right? So it's alternating. So these different layers, I'm guessing, is different layers of metallization and insulators.
And then did they just plop a metal on top, or did they because it looks like it was 3D printed essentially. I'm guessing if you use the gas deposition, it would permeate into the substrate. So how did they get that metal piece to sit on that dielectric?
They grow the metals. Grow the metals meaning like the way they used to deposit the metals is they put the wafer in a metal deposition unit, which is like a metal thin film metal evaporators or sputtering tools. These are basically where the metal is. There's a target on one side. Imagine a big chamber. I'll just draw this. And just warning you, I'm going to give a very hand-wavy kind of description of this. But just imagine that you have your wafer sitting on here. So this is your substrate here. And then it's in a big vacuum chamber. And I'll describe one simple process, which is called thermal evaporation, where you have a crucible that contains a piece of your metal target, the one that you want to deposit, and this is heated. The crucible is heated, and this when it's heated to a temperature, and there's also, there's so many different techniques that are used. One is called E-beam evaporation, where there's an electron beam that's pointed at this thing, and that electron beam helps remove some of the metal ions from here. So imagine that you just have these metal atoms just all over the chamber that you basically remove from that metal target through using E-beam or some kind of thermal mechanism. So these metals can find their way and just deposit themselves on the substrate. So you're literally growing the metal like one atom at a time, and you can grow them to nanometer precision. And by covering up certain regions, let's say I've covered up this most of the wafer, except a few select regions. Now the metal can only deposit themselves in certain areas. So this is how you do pattern deposition of metals, and you keep on doing this process where you pattern a mask, deposit the metal, pattern a mask, deposit the metal, and so forth. And this is just one way of doing it. There's another sputtering technique, which is where you use an electric field to help push the metal atoms towards the substrate. Sputtering and E-beam evaporation are 2 common ways of doing that sort of thing. All right, so let's see. So I mentioned ion implantation. It's a way to control the threshold voltages, the depth and impurity dose can be controlled. All right, so this is an energy band diagram in the horizontal direction. I wanted to just go over this quickly with you. So because all the energy band diagrams we've done so far has been going in the vertical direction, going from the metal, to the oxide, to the semiconductor. So, if this is your gate material, this is your source and the drain and the gate. Most of the energy band diagrams that we've drawn have been going in this direction. We are now drawing an energy band diagram going in this direction, going from left to right. Because this energy band diagram will help us understand the behavior of the MOSFET when we turn it on, and it will allow us to understand an effect called drain-induced barrier lowering. So I just want you all to be able to draw an energy band diagram like this. And the way to draw it is actually pretty straightforward. I'll just go through it step by step. If we're doing an energy band diagram going in the horizontal direction like this, then what you start off with at equilibrium, you start out with EF like this. Okay? And so we have an NMOS device. So you have an N-channel source, an N-channel drain, and then a P-type substrate in the middle. So imagine that in your energy band diagram, okay, I know that this section here is N-type. This section here is N-type. And the region in the gate, just under the gate, is P-type. So I know that this region in the middle here is going to be P-type. So the way I can go about drawing that is I first draw the N-type regions. In the N-type regions, the Fermi level is going to be above EI. Right, so we can draw EC up here. We draw EI over here. And I'm just going to erase these extra boxes. And here's your EV, right? So we do that on both sides. So you have your EI, your EC, and your EV here. And then in the P-type material, the Fermi level is close to the valence band and EI is above that. So you can draw the P-type material here like this. It's kind of like drawing like back-to-back p-n junctions. Okay, so you have your EC, EI, and EV, and now you just connect them together like this. All right, and that's how we come up with the band diagram that you see. Band diagram that you see here. So what does this mean? This is telling us the same thing that we saw on the first slide of this module when we started talking about how a transistor works. If you have an N-type material, a P-type material, and an N-type material, you can't conduct electricity because you have this energy barrier that's formed here. All right, so this is forming a p-n junction here. This is forming a p-n junction here. So if you look at what the carriers are doing, and this is an N-type material. This is an N-type MOSFET. So what you're interested in is what the electrons are doing. Right? You have all these electrons in the source and drain regions. These electrons have this potential barrier here, so they can't overcome this potential barrier. So there's no electrical connection between the source and the drain. But if you were to if you apply gate voltage, you invert this P-type channel and you change it to N-type. And when that happens, then the band diagram looks like this. Your EC just goes straight across like this. Maybe there's a little bit of an energy barrier there. It looks more like this. And now the electrons can go freely back and forth. So by applying a gate voltage, you can see this here, this green arrow here. By applying a gate voltage, you're changing the channel material from a P-type to an N-type. You're essentially dragging down this section of the band diagram in relation to EF, and you are changing it to an N-type material. So therefore, you can conduct electricity. All right. Here's another example of something that I would like you to do at home and practice for the exam. I think I mentioned this before. Definitely there'll be some kind of question on the PMOS device. Conceptual, how it works, physical structure, what are the types of carriers in there, what is the type of the inversion channel, and so forth, the polarity of voltages. because it's a good way to apply your understanding of the NMOS into a different device. All right, let's get into the second order effects in the MOSFETs right now. There's a variety of non-ideal characteristics that come about in a typical MOSFET device. We're going to talk about a handful of them. The leakage currents, short channel modulations, and then the body effect. The first two of these occurs as a result of a short channel effect. Short channel effect. So these effects typically become more pronounced as you're trying to make your MOSFET smaller. And so that's why these two were quite important. And the body effect is something that you may have seen in your previous classes. That's another way to control the threshold voltages. And the body effect happens in both small and large devices. So Moore's law is all about making the transistors smaller, right? This is a slide I also just added. Miniaturization of the transistors has become a science, has become an art. It's become like a really big engineering challenge. For the first 20-some years of Moore's law, when they were miniaturizing, it was they had a very set way of miniaturizing transistors and how to change the transistor parameters to make sure that the transistor works when you make them smaller. And that's what this slide is talking about. There were someone at AT&T Bell Labs, I believe, that came up with these scaling factors. So basically, what these scaling factors are is that let's assume that you shrink the transistor by a factor of k. So if k equals 2, that means you're shrinking the transistor by a factor of 2. The length and the width are both become 1/2 the length, 1/2 the width. You're scaling all the dimensions by this factor. Okay? And in order for the transistor to work as intended, you have to scale other parameters in a similar manner. So I'll talk a little bit about how that works. So let's say you made the length of the transistor and the width of the transistor smaller by a factor of k. So your L and your W of your MOSFET become smaller by a factor of k. So then those, the reason why it says 1/k here is because the new length is the old length divided by the scaling factor. All right, so the new L is equal to the old L divided by k. When you reduce the surface dimensions, the length and the width, it turns out that you also have to reduce the oxide thicknesses. All right, why is that? If you just imagine drawing the transistor like this. So let's say this is our big transistor here. If we want to make the same transistor in a smaller dimension, we have to actually reduce the thicknesses of the gate oxide and the metal. Sorry, I actually didn't reduce the size there. So as you make the transistor smaller in the L and W dimension, I chose the wrong one here. You also have to decreases the thicknesses. So this is the, let me describe what these dimensions are. This is the length of the transistor, and this is the junction width. So this X sub j that you see here, that's what this dimension is. And the oxide thickness, this dimension here, is the D. So what they're saying is like if you decrease your L by a factor of K, you also have to decrease the D and the X sub J by the same factor. And one of the reasons for this is that you want to be able to maintain similar threshold voltages. Okay, and the path for those electrons to go through the device have to be scaled according to the length and the width. Now, if you were to have, let's say you didn't do that, you may end up with a device that looks like this. So you have a short channel device, but you have these massive N source and drain regions, and that can cause an effect called drain-induced barrier lowering, which we'll talk about in a second. The impurity concentrations have to be scaled by K. So you're going to increase the impurity concentrations to increase your threshold voltages. Ideally, the power supplies should also be scaled by K in order to maintain a constant electric field. The electric field is equal to the voltage divided by the thickness of the oxide, right? You're making the oxide thickness smaller, and if you maintain the same voltage, your electric field in the oxide is going to go up. So ideally, what you want to do is reduce the voltage so you can keep that electric field constant, but in practice, that can't always be done. Why? Because like we've been scaling down, let's say back in the 70s and 80s, the transistor dimensions were 10 micrometers, right? 10 micrometers was a typical gate length for the transistor back in the 80s. Nowadays, it's on the order of 10 nanometers. So that's going down by a factor of 1,000. Okay. The typical voltages that were being used in transistors back in the 80s was like maybe something like 5 volts. If you went down in your voltages by a factor of 1,000, what would that leave you with as for your threshold voltages? 5 millivolts. 5 millivolts, it would be very difficult to control transistors if your threshold voltages were 5 millivolts. Because 5 millivolts is like, if you put an electrode on your skin, you can get 5 millivolts of signal out of it. It'd be very difficult to control the on-off state of the transistors. So we've only gone from like 5 volts of threshold and power supply voltages down to maybe like 1 volt. And like less than 1 volt in some cases. We can't go down much further than that because of the noise could cause the transistors to go on and off. So we haven't done the ideal scaling. We haven't scaled the power supplies by K as ideally you would do. So as a result of that, the electric fields in our devices are much larger than they were before, and that can cause effects like hot electron effects and short channel effects. Some of those things we can talk about right now. But these are in general the ideal scaling rules for a MOSFET. Okay, the main things that I want you to know about is that the oxide thicknesses and then the source drain thicknesses should scale by 1 over K. Impurity concentrations should ideally scale by K, so they should increase as you make the transistor smaller. The currents and voltages go down by a factor of K, but the current densities go up by a factor of K. And the rest of these, don't worry too much about these other ones. The reason why the current density part is important, if you make your transistors smaller by a factor of 1,000, which is what has essentially been done over the last 30 years. We've gone from 10 microns to 10 nanometers. The current densities have gone up by that much. Yes. There's more transistors operating, and you have smaller paths for the electrons to travel through. So as a result of that, heat dissipation has become a huge problem. And you'll see that one of the major issues in transistors right now, in basically CMOS design right now, is that the amount of heat that's generated by these high power microprocessors, which have tiny transistors, is a big big issue, and that's why I think I showed you on the first day of class why Google has in their data centers, they have these massive water flow, coolants flowing through their servers. So we'll talk about some short channel effects in MOSFETs right now. So some examples is hot carrier generation. So hot carrier generation, I don't know if this diagram describes it that well, but when you have a transistor in saturation, you know that there's this pinch-off region, right? There's a pinch-off region when the transistor is in saturation. That pinch-off region has a high electric field. Okay, when you make the transistor smaller, as I mentioned, the electric fields get even stronger than they were. As you're scaling down, your electric fields are becoming larger and larger. And one of the effects of this is that you can have electrons gaining so much kinetic energy from the electric fields is that they can actually embed themselves into the silicon dioxide substrate. They can actually generate electron hole pairs by slamming into another atom. Okay, so that's what this is showing here, a pair creation, and that can create some substrate current. If the electron embeds itself into the oxide, which it can do, the electron has so much energy that it can actually just slam into the oxide and it ends up staying there. That results in oxide charge, and that will change your threshold voltages over time. So that hot carrier generation is one issue in short channel transistors. Another one is drain-induced barrier lowering. That's the next slide, and then thin oxide breakdown, which results in leakage currents. So let's look at the drain-induced barrier lowering first. This effect is the result of overlap between the source and the drain depletion regions. So this diagram sort of shows it, but I think I'll just, if I can draw it again here, I think it'll be a little bit more clear. All right, so in a typical MOSFET device, you have your source, drain, and gate. And then here's your substrate. It's a p-type substrate. Now, if you remember from the diode chapter, what happens at the interface of a p-type and n-type material? Over here, where my cursor is. A depletion region is formed, right? Okay, so let's just draw that in there. So there's a depletion region on either side of the interface. Okay, and the same type of depletion region forms here as well. Okay, that's a very important component of a MOSFET that we have to think about. Normally we're saying like, okay, we're only concerned about the conductive channel between the source and the drain. Okay, what happens just underneath the gate? That's true. That's where the majority of the interesting stuff happens, but we also have to consider the fact that we do have depletion regions around the source and the drain. If we bring the source and the drain very close to each other, those depletion regions actually start to overlap with one another. Right? I don't know if you remember, we calculated some depletion region widths. They were on the order of a few microns in some cases. Okay, and now, as you know, the typical length of the transistor is well below 1 micron. It's like 10 nanometers to 100 nanometers. So these depletion regions start to overlap. And that's what this slide is showing here. All right, so this line that you see here, this line is kind of like the depletion region in the P side of the substrate. And because the source and drain are so close to one another, so those depletion regions have begun to overlap. So what does that do? It makes the channel region. So if we look at the just underneath the gate, the gate has a depletion region throughout the channel already, right? It already has a depletion region there. So what that depletion region does is that it creates this, it already creates some of the negative charge, creates negative charge, and to compensate for that negative charge, you have to add additional charge into the gate. So it changes your threshold voltage. Actually, that's the first effect. But the second effect, which this drain-induced barrier lowering, is responsible for one of the key behaviors of a transistor at saturation, and that is the short channel effect. So we're going to focus more on that. So when the transistor is off, this drain-induced barrier lowering phenomena can cause leakage currents between the source and the drain. And let's look at why. A few slides earlier, I showed you this diagram here. And I said, like, okay, well, when the transistor is off, the electrons have this barrier, okay? This barrier here, and that barrier prevents the electrons from going, from going back and forth between the source and the drain. There's no contact, there's no conduction between the source and the drain when the transistor is off because of this barrier. If this barrier didn't exist, then the transistor would be on. So essentially, what this drain-induced barrier phenomena, what it does, it actually reduces that barrier height. Okay, and if you think about it, it makes sense. Why? Because the channel, when you've overlapped the two depletion regions, there's no p-type material in between them. It's all depletion region in the middle. If you don't have that p-type material in the middle, you don't have a good barrier in your energy band diagram. So the way that's shown in an energy band diagram is like this. The blue line here shows what the energy band diagram would typically look like when you have applied a voltage between the drain and the source. And I just want to point out that if you don't apply, this is what the band diagram looks like. The electron potential energy looks like this at equilibrium. So EF. So this is what, this red line here is what the electron potential energy looks like at equilibrium, when EF is flat all the way across. If you apply a potential to it, then it looks like this. Because now you have an EF on this side and a different EF on this side. When you apply a potential between the source and the drain, you have two different EFs. And so the band diagram looks more like that. And that's what's being shown in this plot here from the book. If you don't have drain-induced barrier lowering, the electron potential energy looks like this, the dotted blue line, the long channel. All right, and you notice that there's this barrier here. This barrier is the same barrier as before. It's that transition from an N-type to a P-type material. And that barrier actually prevents electrons from flowing from the source to the drain at when you have no gate potential, when you have no inversion. But this drain-induced barrier lowering effect makes the potential look something like this. There's not as much of a barrier. It reduced that barrier. As a result of that, there can be some electrons that flow back and forth between the source and the drain, even when the transistor is off. What is this going to do to power consumption in a microprocessor? Those of you who've taken courses in computer architecture or digital logic, what happens if you want your transistor to be off, you want your NMOS or PMOS device to be off, but it's not actually off. There's actually current between the source and the drain. What's that?
Increases the power.
It'll increase the power consumption. That's right. And so that'll reduce the battery life of your instruments, of whatever microprocessor you're using. So that's something we don't want. this I on to I off ratio for a transistor is very important. When the transistor is off, you do not want any conduction between the source and the drain. This drain-induced barrier lowering reduces the I on to I off ratio. All right. The second thing it does is that it causes an electrical modulation in the width of the channel. So this effect, have any of you seen this before, the channel length modulation effect in transistors? Okay, some of you haven't, it's okay. Channel length modulation is a very common thing that you'll see in transistors that have channels less than a few microns in channel length. It's also called the early effect. So some of the undergraduate textbooks refer to it as the early effect. So what you see in the black lines are the ideal curve of a transistor in saturation and in triode region. So as if you remember from before, this region here is this is the triode region, and once you get to the saturation region, you expect to see a flat line, a horizontal line. But this short channel effect, the channel length modulation effect, due to drain-induced barrier lowering, causes the channel length to decrease with larger voltages. As a result of the decrease, the current goes up slightly. Okay, so it talks a little bit about it here. You know, as you increase VDS, the channel length actually turns out to, the effective channel length decreases a little bit, and that causes an increase in the drain current. All right, and as a result of that, you have to account for that in your saturation equation. So in a typical exam question, you know, if I might tell you to just ignore short channel length modulation effects, and in that case, you can just use the typical saturation equation like this that you see on the left. If you are asked to include channel length modulation effects, you have to know this lambda parameter, and that lambda parameter would typically be given to you. And then based on your VDS, you can calculate this extra term. And that extra term accounts for the extra current, the small amount of extra current due to the short channel effect, the channel length modulation effect. So this lambda factor is more pronounced in small transistors. So it's larger in small transistors. Any questions about the channel length modulation effect? Okay, and let's talk about two more effects. I think we have enough time to cover that. The body effect, and then the gate leakage effect. So the body effect, I just want to preface by saying this effect is not limited to short channel transistors. It exists in long channel transistors as well. So this is what happens if there's a voltage being applied between the source and the body. So let me just draw that out here. So let's say you apply a body voltage here. Then you have your VG being applied here, you have your VS being applied here, and then the drain voltage is here. So let's talk about like what the body effect is. In all the previous diagrams that I've been showing you, we've always been placing the body at ground, right? Always place the body at ground, and the source was also at ground. The source and body were tied together to the same voltage. And that's what's typically done in an NMOS type device. In a circuit, you'll often see something like this, where the NMOS device is, the source is tied to ground, and then this body will also be tied to ground. And this is the body terminal that they talk about in the transistor. So when you apply a VGS, if you apply a VGS to the gate, you'll be applying a gate voltage to the body as well. right? The body is grounded, the source is grounded, so applying a VGS is like applying a VGB. So what happens if the body is placed at a different voltage? It turns out that this changes the threshold voltage. So, in fact, in some cases, applying a body voltage is intentionally used to change the threshold voltage. If you can't get your transistors to work because the threshold voltages are off, you just apply, you stick the wafer, you put a voltage on it, and it'll change the threshold voltages for all the transistors in your system. So it's a quick way to do that, and it relies on something called the body effect. So first of all, what is the polarity of voltage that we want to apply to the body? So let's remember that this is a P-type substrate, and then you have an N-type source. So this is an NMOS device. What'll happen? Can someone tell me what'll happen if we apply a positive VBS? Let's say the body voltage is greater than the source voltage. What'll happen? I want you to look specifically at this PN junction here.
Forward bias diode.
You forward bias the diode, exactly. So if you forward bias the diode, you're going to get a ton of current flowing from the body to the source. That's not what you want. Right? That's not the you want MOSFET-like behavior. You don't want like a diode between the body and the source. Okay. So first things first is that the polarity, you always have to apply a polarity so that these PN junctions are never forward biased. They always have to be reverse biased or at equilibrium. So you're going to apply, for an NMOS device, you're going to apply VSB, meaning the body voltage is going to be negative. So let's just indicate here that this is going to be negative. Now, if we apply a negative voltage here, what's going to happen is shown by these equations. If you don't apply a body voltage, the width of your depletion region is given by this equation. If you apply a body voltage, a VSB, then the depletion width increases by an amount equal to the square root of VSB. You have the second term here that you've added. Okay, that's the way to remember kind of mathematically what's happening there. Intuitively, what's happening, if you think about, if you apply a negative gate potential to the body, in the energy band diagram, that's essentially, it's creating, it's increasing the Fermi level. It's increasing the Fermi level on the body side. So that's going to cause more bending in the band diagram. As a result of more bending, it's going to create a wider depletion region. There's going to be more depletion charge in the body underneath the gate. As a result of there's more depletion charge, there's more charge is required to achieve inversion. So your threshold voltage is going to go up. And the best thing to do is just try these problems. Try some of these problems at home. One of your homework questions has to do with calculating the threshold voltage after a body effect has been applied. So it increases the threshold voltage for an NMOS. It decreases the threshold voltage for a PMOS device. Okay, and this equation here gives you the delta VT. Delta VT is the change in threshold voltage compared to if you didn't have the body effect. All right, and the last effect that I want to talk about today is leakage currents due to oxide tunneling. There's two types of tunneling mechanisms, and the context I'm going to give you right here is, remember I said that when you're scaling the transistors, you're making them smaller. You have to scale the gate oxide thicknesses as well. So the gate oxide thicknesses become thinner and thinner and thinner. And one of the issues with having very thin gate oxides is that you have this thing of oxide tunneling. The way that oxide tunneling looks like in an energy band diagram looks something like this. This is the metal is on the left, then you have the oxide in the middle, and then you have the semiconductor on the right side. So let's look at direct tunneling first. The oxide is a region where there should be no states. There's no states within the oxide that a charge carrier could go through. And that's the reason why it behaves as an insulator. Charges get stuck on one side. They can't go through the insulator because there's a large energy barrier that it has to go over. That's what this energy band diagram is showing here. But if the oxide layer happens to be super thin, when it becomes very, very thin, the probability of tunneling means going through a region of no energy states and finding energy states on the other side of it. If the oxide layer becomes very thin, then the probability of tunneling goes up exponentially. So, if you have super thin gate oxides, then you can have this issue. You can have a probability that charges go through the gate into the body of the transistor, and that deviates from the ideal behavior of the MOSFET. You will get gate leakage currents. Gate leakage currents will also increase the power consumption of your MOSFET device. Yes?
So does having the body effect increase your chances of having this first type of tunneling effect as well?
So the question is, does the body effect increase the probability of tunneling? And what's your thought process behind that?
Well, I think that with the body effect, you're always increasing the electric field. Basically, that's why you have such an issue overcoming your problem there with the body effect. So that would mean, I would think that you would be more likely to have issues with tunneling.
Yeah, you're absolutely right. This is electric field dependent. So if you are applying a negative voltage to the body, you're essentially increasing the electric field through the gate oxide, right? You have a larger voltage difference between the top of the gate and then the body underneath it. As a result of that, yes, you will increase the probability of tunneling. Yeah, it's a good observation. There's two types of tunneling. I just want to mention this real quick because we're coming up to the end of class here. There are the direct tunneling is going all the way through the gate oxide in one event. The second type is going through different states in the gate oxide, and this one turns out to be electric field dependent. This one is not electric field dependent. So they have slightly different equations that describe them. Now, you're not going to be asked to calculate any tunneling currents. Really, I just want you to understand the basic mechanism and how it plays into the manufacturing, which is basically that, like thin gate oxides, you can have more gate leakage currents. So in this diagram, you can kind of see that the electron goes through a portion of the SiO2, but then there are some energy states up here. Remember, if this is the band diagram of the oxide, then oxides can have a conduction band too. They just have a very, very large band gap. If you apply a very strong electric field, there can be enough bending in this diagram where you could actually have be tunneling through a portion of the silicon dioxide, and then there are some states there that it can go through as well. Whereas this one is going all the way through the oxide in one fell swoop. Okay, so I think I'll leave it at that for today. I was hoping we'd get into some of the manufacturing processes, but we'll talk about that next time. So I'll talk to you about how you can do a basic fabrication of an NMOS device next time. This table will help you in your homework. It's just a summary of the different equations that are used for an NMOS and PMOS device. Again, like I posted the homework today. I know you have your projects going on right now, but I highly suggest that you take a look at some of the problems between now and Wednesday, so that you can ask some questions on it, because Wednesday will be the last class before the exam. Okay.
So these are the newly updated slides, right?
Yes, I'll post the newly updated slides. Even if you use the old ones, it's probably fine because there's just a couple slides that were changed. But I'll post the updated ones for any of you who want to keep.
And then, did you say the solutions for both boards are going up on Wednesday?
The solutions for the diode chapter have already been posted. The solutions for the MOSFET ones will be posted on Wednesday.
Oh, cool. Nice.
Yep.